In example number 5, we're going to use Newton's law of cooling. Newton's law of cooling is the following. The temperature of an object, T, in surrounding air with temperature Ts, that's the surrounding temperature, will behave according to the formula. T of T, which is equal to A e to the kt plus the surrounding temperature, where T is the time, A is the difference between the initial temperature of the object and the surroundings, and K is a constant, the continuous rate of cooling of the object. Now, how do we go about this? Well, given a set of conditions to apply Newton's law of cooling, number 1, we're going to set the surrounding temperature equal to the y-coordinate of the horizontal asymptote, usually the ambient temperature, and then we're going to substitute the given values into the continuous growth formula to find the parameters A and K. And then step 3, we're going to substitute in the desired time to find the temperature, or the desired temperature to find the time. So for example 5, a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35 degrees Fahrenheit refrigerator. So the surrounding temperature that it's placed in is 35 degrees. After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. If we must wait until the cheesecake is cooled to 70 degrees before we eat it, how long will we have to wait? Now, because the surrounding air temperature in the refrigerator is 35 degrees, the cheesecake's temperature will decay exponentially toward 35 following the equation. So now we're going to plug in T subscript S as 35. Now, we know that the initial temperature was 165. So at times 0, then the temperature is 165. So we're going to plug in those values into that function. So T of T is 165 in step 2. T is going to equal 0. So we have 165 is equal to A times e to the power of 0 times k plus 35. Well, 0 times k is 0, and e to the 0 is going to be 1. So 1 times a is going to leave us with a. And so now we can just rewrite the equation. So it's a plus 35, which is equal to 165. And we could subtract 35 to both sides. And now we figured out that a is going to equal 130. Now, we were given another point because it's telling us that after 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. So now we can go ahead and find the value of k by plugging in that other point. So T of T is going to equal 150 and T is equal to 10 now that we know the value of A. So we have 150, which is equal to 130, e to the power of 10k plus 35. So we subtract 35 to both sides to get 115, which is equal to 130 e to the 10k, and then divide both sides by 130. And then we're going to take the natural log of both sides. So taking the natural log of both sides allows us to be able to then factor and solve for 10k. So to solve for 10k, we're going to divide both sides by 10. And so k is going to equal 1/10 times the natural log of 115 over 130, which is approximately negative 0.0123. And now we have our equation model for the cooling of the cheesecake. It's going to be T of T, which is equal to 130, e to the power of negative 0.0123 t plus 35. And now we can solve for the time it will take for the temperature to cool to 70 degrees. So, in order for us to find the time, we know that T of T is going to equal 70, and then we're going to use our combining like terms and logarithm rules to solve for T. So we're going to subtract 35 to both sides, and then we're going to divide both sides by 130. So now we have 35 over 130, which is equal to e to the negative 0.0123 t. Then from here, we're going to take the natural log of both sides. And so taking the natural log of both sides, we have negative 0.0123 t. It's going to equal the natural log of 35 over 130. And dividing both sides by negative 0.0123, we get t, which is equal to this order of operations, which is approximately 106.68. So therefore, it will take about 107 minutes, or 1 hour and 47 minutes, for the cheesecake to cool to 70 degrees Fahrenheit.